My name is Stuart Carlton. I am Healthy Coastal Ecosystem Specialist with Texas Sea Grant, and we're really excited to present the next in our Coastal Hazards Adaptation Success Series, a bunch of webinars that we're doing about different ways that people are coping with coastal hazards broadly defined. And for today, we're going to have a nice talk by Dr. Nailun Fernando of the Texas Water Development Board. She is a hydrologist in their Basin Estuary program, and she is really passionate about promoting science for decision-making and water management, and about tailoring her research products, to match user needs. In her current role, she is responsible for producing coastal freshwater inflow data sets, simulating runoff in ungauged coastal subwatersheds along the Texas coast, and producing and improving seasonal rainfall and reservoir evaporation rate forecasts from May through July over Texas to aid in drought planning. She was the principal investigator on a recently completed project funded with a U.S. Bureau of Reclamation Drought Resiliency Grant through the Texas Water Development Board to develop an online tool to aid drought contingency planning in Texas. And I believe she's going to talk about some of that work today. And she holds a PhD in geography from Rutgers and an MA in climate and society from Columbia, and a BA in geography from the University of Colombo in Sri Lanka. And so we're really excited to have her here.
Thank you, Stuart, for that introduction, and thank you for this opportunity to be able to present for the Texas Sea Grant webinars. As Stuart mentioned, the work I'll be presenting today is what we did with funding from the U.S. Bureau of Reclamation. We recently produced an automation of the May through July rainfall forecasts, and these are available on our Water Data for Texas website, and I'll get into the nitty-gritty details of all that in this talk. Before I move forward, I'd like to acknowledge two folks who were collaborators on the project at the Water Development Board. That's John Zhu and Solomon Neguse. And we've been collaborating with Dr. Rong Fu out of UCLA. She used to be at UT Austin, and we've been working with her on drought diagnostics over Texas since 2011. And two folks from the Brazos River Authority, Chris Higgins and Aaron Abel, since 2015. Here's an overview of what I'll be touching on today. I'll start off with a brief introduction to drought in Texas and explain why the May, June, July season is important. Then I'll delve into how water planning is undertaken in Texas and how drought contingency planning fits into the metric. Then we'll look at what forecasts are, the key lead times, and what decision time scales are with respect to forecasts time scales, and then what the basis for predictability is. And then go into the May, June, July rainfall forecast tool that we developed, and an application for reservoir storage forecasting that we undertook. And then I'll end up with lessons learned and planned work. As Stuart mentioned, please feel free to interrupt me if you have questions as I'm going through the slides. So to get on to drought in Texas, let's start off with 2011, which is probably very much alive still in your memories. I'm hoping that the recent floods haven't erased the memory of that bad drought in 2011, which happened to be the record one-year drought for Texas. Something that was a characteristic of that drought was that it intensified rapidly in the spring. However, that intensification was not forecast, and the figure on your left shows the May, June, July rainfall forecast issued by the National Oceanographic and Atmospheric Administration, issued at the beginning of April. And what you see is in browns, the area where it was likely going to be below normal, so dry conditions were along the coast, but the probabilities were about 40% only, not really enhanced. Anywhere you see whites means it was an equal chance of either it being below normal, near average, or above normal, but we really didn't have any skill in the forecast. So we wouldn't have known ahead of time that the drought was going to intensify so rapidly in these months. On the right side, you see what actually was observed. The deep reds show areas of the state which had actually the record driest season for that year. And then for the rest of the state, it was much below normal, the oranges. So what here is the problem? Most dynamical models that are used for forecasting have a difficulty capturing rainfall accurately for this critical time period. I'll get back to that point shortly. Let's get on to why we considered this season to be important. So we looked at strong summer droughts in the past, going back to 1895. And what we found was that 92% of these strong summer droughts had lower rainfall in the spring. And what happens with a dry spring is that you have a high pressure system set up over Texas in the middle troposphere. That's roughly about 5,500 meters above sea level. And that means that there's going to be less likelihood of frontal systems bringing in storms or even convective rainfall occurring over the region. And it also means that it's going to be a lot warmer over the region. The south central part of the US has been identified as a hotspot for land atmosphere interaction. There's a paper by Costa et al. I think it was 2004, but I can clarify that and send that information to Stuart. But what the key message here is that if it is drier, it's very likely going to be warmer over the south central US during this season. So if you have a dry spring and it sets up that high pressure system, you're going to have downward motion or subsidence rather than uplift, which is good for rainfall. So you have a sinking motion and a further reduction in rainfall, which is going to make it even hotter. And so the cycle persists through the summer until this change of season in fall, when you have cold fronts coming in and reducing the warmth and then breaking the high pressure system and finally allowing for storms to come through and such. So if we know what's going to happen in the spring, we have a good and quite a good understanding of whether it's going to be dry or not in the summer. So that's something I'd like you to keep in mind as we go forward. So why is the Texas Water Development Board concerned with drought information? The TWDB is the state agency tasked with developing and securing water for the state. It prepares a state water plan based on 16 regional water plans. The map on the right shows you what those 16 regions are. The state water plan is meant to address the water needs of all water user groups across the state during a repeat of the drought of record. The drought of record for most of the state is the 1950s drought. However, for a few parts of the state, the 2010 to 2015 drought, the more recent drought, is the drought of record. But for now, planning is undertaken using the 1950s drought of record as the rule. After 2011, there were modifications to the Texas Administrative Code, which said that plans must consider drought conditions in the near term. So the state water plan plans out to a 50-year time horizon. So it's a long-term planning initiative, which is updated every 5 years. However, after 2011, because there was a dramatic reduction in reservoir storage and such within a period of, say, 5 months that was not anticipated that year, there was a recognition that there needs to be preparedness for short-term steps that could be taken to reduce demand when we know that there is a drought afoot. So as I said, the post-2011 drought modifications meant that water user groups need to have drought response triggers for all their water sources. An example of a water source could be a surface water reservoir, it could be a groundwater well, but so each user group has identified where their water sources are, and then for each source they need to have response triggers. That means if it goes below a certain level, they need to initiate, say, voluntary conservation measures, or if it goes down even further, maybe initiate mandatory water restrictions, etc. So these user groups, in addition to having response triggers, they need to have a drought water management strategy that plans for demand reduction in the near term. And in order to be able to implement drought contingency plans, there needs to be information on forecasted or persistent drought conditions. Let's take a look at what forecast timescales are and what typical decision timescales are. This plot I've taken from the National Academies of Sciences and Engineering and Medicine 2016, their new report on next generation Earth system prediction, strategies for sub-seasonal to seasonal forecasts. The decision timescales are on the x-axis, and the different types of forecasts lead times are on the y-axis. So anything that you see in red refer to decisions that are taken in the near term. For example, within a week time scale, you can think of FEMA evacuations, like for flood. It could be weather alerts for aviation, etc. Given that we are interested in the seasonal time scale, that would be 3 to 9 months out into the future, the decisions that are affected at that time scale would be things like planning for water allocation during a drought, managing reservoir levels for flood control, and then on the agricultural side, purchasing seeds. On the energy side, planning for spikes in energy demand, managing hedging in future markets, etc. So I just wanted to go through this figure so that people have an idea of what kinds of decisions are dependent on climate forecast, weather and climate forecast at different timescales. So the black the decisions in black lettering refer to the longer time scale, where climate projections that would be beyond, say, 20 years from now, those have any impact. So on the water time scale, water sector, it would be planning for new reservoirs. And on the energy time scale, it could be building new power plants or figuring out how to distribute energy, etc. And then on sources of predictability at different timescales, this is a plot that I've taken from the National Research Council's 2010 publication on assessment of intra-seasonal to interannual climate prediction and predictability. The red box shows the timescale of interest at the seasonal timescale. And you see that there are a number of processes that interact during this time scale. It could be soil moisture, sea surface temperatures, volcanic eruptions, aerosols. At the shorter time scale, there are things like the convectively coupled equatorial waves, etc. And on the y-axis, what you see is how different parts of the atmosphere, ocean, and land interact with each other in terms of determining predictability. In this slide, I just wanted to highlight the ones that are important for the seasonal forecasting and the drought prediction time scale that we are talking about. So primarily soil moisture, sea surface temperature anomalies, such as those associated with the El Nino Southern Oscillation, and then atmosphere-ocean interaction and atmosphere-land interaction. Like the key processes that we need to keep in mind as being important for this time scale. So remember when I showed the forecast from NOAA for 2011, I mentioned that dynamical models have difficulty in capturing the spring and summer rainfall signature. The reason for that is that the rainfall processes during this season are primarily convective, and they occur at spatial scales smaller than the current resolution of dynamical models. So the models really do not do well at predicting rainfall during the season. However, they do perform well in capturing large scale patterns, such as the wind patterns or the geopotential height patterns, etc. So what we did was we based on our assessment of physical drivers of drought in the May, June, July season, we realized that there are three main predictor variables, as it were, key processes that tend to be active when we have a reduction in rainfall during this season. So the key processes, I've said that these are also predictors used in the forecast model. The mid-tropospheric high pressure system at 500 hectopascals, enhanced convective inhibition energy, which means it's the atmospheric column is not conducive for rainfall to occur, and low soil moisture. So using these three predictors, we forecast rainfall over Texas and the South Central US, and we found that it actually does quite a good job at capturing the past dry events. So what I want you to remember as a take-home message is that the failure of the May, June, July rainfall season is associated with intense summer drought in this region. Therefore, forecasts of May, June, July rainfall serve as early warnings of impending summer drought. I mentioned that the statistical forecast that we built was quite good at capturing the past events. This slide shows you some measures of skill. By skill here, we refer to how accurate was the forecast with respect to what was observed in the past. The figure on the top, which is the Spearman correlation, provides an assessment of how good the deterministic forecast, that is the actual rainfall value, was compared to observed. Typically, when a seasonal forecast is issued, we provide the information in terms of a probabilistic forecast of whether it's going to be above normal, near normal, or below normal. Because providing a deterministic forecast can it can appear that we have a lot of confidence. We give an exact number for the volume of rainfall, but because we know that there is a lot of uncertainty in the forecast, it's preferable to provide the forecast in probabilistic terms. So the second skill metric, which is called the ROC area, which is relative operating characteristics, and the 2AFC skill, these two skill metrics look at the performance of the model at getting the three categorical forecasts correct. So anywhere you see oranges or reds, it means that the forecast is doing a good job in terms of it's a higher skill. And the take-home message for this is that forecast skill levels exceed skill due to persistence or autocorrelation over most of Texas and Oklahoma. So that particular finding was helpful in indicating that the statistical forecast has some added value over using purely persistence as a forecast. Given that the forecast had reasonable skill and it had the potential to provide some information that could aid with drought planning, we decided to automate the rainfall forecast and provide it in a form that users could access whenever they were interested in doing so. We got a grant from the US Bureau of Reclamation's Drought Response Program in 2015, which was a 2-year grant which just ended, and that allowed us to go ahead and provide county-level forecasts of May, June, July rainfall. And these forecasts are issued from January 16th through May 1st with updates every 2 weeks. The predictors that are key for May, June, July rainfall have the strongest signal in April. I think in the slide previously I didn't mention that, but it is the April values of those 3 predictors that we use in the prediction of May, June, and July. So you might wonder, how is it that we provide forecasts from January 16th through March if we are using April April predictor fields? So what we do is we use forecasts of April predictor fields issued from NOAA's Climate Forecast System version 2 or CFSV2 operational dynamical forecast model for April circulation fields. And then for forecasts made from April 16th, on the 1st of April and 16th of April, and the 30th of April, which is actually the May 1st forecast, these are based on actual observations. So the tool that we developed actually provides some lead time information. So from January onwards, we can get some feel for whether the summer is likely to be a year with drought or not. So that gives some added information for sectors that need more than, say, 3 months lead time to take decisions. We also applied the forecast for May, June, and July to get experimental reservoir storage forecasts for 3 reservoirs on the Brazos River Basin. This was primarily to have a proof of concept for which water managers in Texas could use climate information to implement drought contingency plans for surface water sources. We also applied it to generate reservoir evaporation rate forecasts. Today I'll be talking only on the reservoir storage forecasts. And if anybody's interested in learning more about the reservoir evaporation rate forecast, I can provide a link to that. Here is a screenshot of the rainfall forecast tool. I put drought in inverted commas because, as I said, if we know what's happening in the May, June, July season, we have a good indication of whether we're going to have a summer drought or not. The URLs for the forecasts and background information on the forecasts are provided on the screen. So as I said, these are county level forecasts, and this is not a live demo, but if you click over one of these counties, you're going to see a drop down showing you the probabilities associated with the 3 different categories: above normal, below normal, near normal. And if you click on if you hover over it, you get those 3 categorical forecasts. If you click on one of the counties, you're going to get a probability of exceedance curve. I'm going to get into that detail in just a little bit. I wanted to provide an estimate of skills for the forecast, just in case folks are interested in how well this actually performed and would like to have some scientific assessment of what the skill is. So the prediction on the figure on the left shows what the prediction was issued at the beginning of the end of April, and then the figure on the right shows the observed category. So it was pretty much near average summer in that you don't really see very dark reds, which would have been below normal, or very dark blues, which would have been highly above normal. In terms of overall skill, which is measured using a metric called Heidegger skill score, we get a 0.48. And then another skill score, which looks at how well the forecasts perform for the three different categories of below normal, near normal, and above normal. For below normal, it was 0.24, for near normal, 0.13, and for above normal, 0.34. And if you're wondering, what does this really mean? On the right-hand side, I've given a little box showing you the different levels of skill and what they translate to. So if you have a skill level from negative infinity to 0, that means it's a skill worse than climatology. And if anyone is wondering what we refer to by climatology, that means a long-term average for that season. And if we get a skill of 0, that means we really don't have any information above that we couldn't have gotten if we used climatology for that season. If it's a scale of 0 to 1, the scale is better than climatology. That means that we have some useful information here that could be applied for decision making. In terms of skill level 1, that would be a perfect forecast, which really never happens. So a good skill would range up, I would say the best skill is about 0.65 or 0.7. But anything beyond that would be a little bit too optimistic and a bit too good to be true. So as a ballpark, think of 0.6 as being a good skill level. So in terms of the overall skill, the forecast was reasonable in terms of it getting 0.48. And for above normal, it was a bit better than for below normal and near normal. Okay, now you might wonder, how is it that we use a seasonal forecast to plan for drought contingency, or planning to implement drought contingency triggers in surface water reservoirs? So the seasonal rainfall tool provides county-level information on impending drier than normal conditions. Such information can be fed into models that are used to allocate water from surface water reservoirs. And we know that regional water planning regions need better information to implement those drought action triggers. But there were some questions that arose when we were trying to figure out what was the best way to go about applying the rainfall forecast to storage forecasts. The first was, how can the forecast be applied to the Water Rights Analysis Package, or RAP, which is developed by Dr. Ralph Forbes at Texas A&M, which is the tool used in Texas for water rights permitting and planning. So we really need to work with the tools that are currently used for water planning if we're going to have provide something that's useful to the state. The second question was, how can probabilistic forecasts of above, near, or below normal be translated to information that a reservoir operator can use? The problem being that a categorical forecast really does not provide any information of how much drier it's going to be. That is, there's no information on drought magnitude. Even if you have a high probability for below normal rainfall, it doesn't give you any information that it's going to be, say, in the 10th percentile or the 20th percentile of rainfall for that season. And without that kind of specific information, water managers really cannot use the forecast for storage forecasting. So steps to address these questions was, we used the conditional reliability modeling, or CRM option in RAP, which was a feature that was implemented post-2011 to support drought planning and short-term operational management of reservoirs. We used the extended hydrology for the Brazos WAM, which would be 115 years of data. And we generated CRM simulations for 3 months, starting from May 1st for 115 years historically. So here we have then historical simulations of storage which reflect the diversions that were projected for 2017. That means that we have the historical simulation adjusted for what the Brazos River Authority told us were very likely going to be diversions from that reservoir, those reservoirs for those 3 months of 2017. And initial storage was set at April 30th conditions. The 3 reservoirs we looked at were Aquila, Limestone, and Proctor. I apologize for the really small font on the map to your right, but let me just point out, Proctor is the westernmost lake, Aquila is in the middle, and Limestone is the lake to the east here. So the thinking behind using 115 years of historical storage adjusted for diversions of 2017 is that storage would reflect all possible rainfall scenarios for those 115 years. And based on that understanding of where, or rather say, if we have high storage, it was very likely to be a year in which there was a lot of rainfall and vice versa. So then how do we factor in the rainfall forecast? Here I use the term information used. So I mentioned that when you hover over the county, you get the probabilistic forecast. I've taken a screenshot for Hill County, which is the county in which Aquila Lake is. So you're going to get a probabilistic forecast of whether this season is going to be above, near, or below normal. So, all the equal probability is 33%. But if you take a look at the 3 categories here, it's marginally below normal. But if you see this kind of 38, 28, 33, it's pretty much in the near normal category. And then if you click on one of the counties, you're going to get the probability of exceedance curve. And this is a bit of information that provides a reservoir operator with information of the rainfall value that is forecast, and going back historically, what was the likelihood for that rainfall to be exceeded this year. So that then ties in the probabilistic forecast and the deterministic forecast that can aid in the decision, in the storage forecasting mechanism that we develop. So we provide this, the green dot here shows what the forecast rainfall was, and we also provide an estimate of an upper and lower bound for that forecast using a 60% confidence interval. And if you click on this, how to interpret the graph, it gives some additional information on what exactly is included in this plot. And here's a close-up of that plot because the other one was really small. So you have the probability of exceedance and the rainfall, and then the green dot is the forecast. And then it repeats the categorical forecast on the bottom right. And here you get the upper and lower limit of the forecast. And then these are the steps that a reservoir operator would take if they were going to factor in the rainfall forecast. So they'd get the point forecast for the county in which the reservoir is located, including the exceedance frequency and an upper and lower limit of the forecast. They would then multiply the historical storage simulations generated from the conditional reliability modeling effort by what's known as a teleconnection factor. This is by, there's a paper by Verbs et al. 2012, provided a citation for that, which talks about what this teleconnection factor is. Simply put, it is an indication of how stream flow might be affected due to near-term climatic conditions. So if you have a QX, if the forecast says it's going to be quite strongly below normal, so say you've got like a 50% probability of below normal, you're going to multiply the CRM output by say 0.75 or 0.5, anything less than 1 pretty much. And if it's an average, a forecast for average conditions, then you'd multiply by 1, meaning that there's really no change in the historical output. And then if you have a wet forecast, that is probabilities of greater above normal, you would multiply by 1.25 or 1.5. So it's like a weighting of the historical storage based on what we know is going to be the large scale signature for seasonal rainfall in the coming season. Next, the historical storage is ranked in ascending order to obtain storage exceedance frequencies. And then based on the exceedance frequency for the rainfall forecast, which is information provided in the probability of exceedance plot, we would select the exceedance frequency of storage. And then the upper and lower limit of the forecasted storage would be also based on the exceedance frequency for the 60% confidence interval of the point forecast. Now, the confidence interval that's used can be varied based on user need, but in terms of a proof of concept we wanted to show that this is something that could be done. And here is a result for just a killer. The forecast lines are the dashed lines, and the black line is what was observed. So it's from this point onwards, so post 4/30 to 2017 that we are interested in. The black dashed line is what we forecast, and the upper and lower limits are the gray dashed line and the brown dashed line. And the yellow, orange, red, and brown lines are the different contingency trigger levels for Lake Aquila. What we see is that the forecast was marginally above what was observed in May. It then dips down a little bit below what was observed in June and July, but it doesn't go, the observed doesn't go anywhere near even the first stage, the first drought contingency trigger. That's because most of these reservoirs were in flood pool this year. So there was really not a risk of any of the drought triggers being reached. But if we have a dry year, this forecast could potentially give advanced information on the likelihood of those trigger levels being reached. We have some planned improvements that we'd like to work on. So the forecast that we provided is a block 3-month forecast, but it is not updated from May through July. But we know that there are instances when you can have flash droughts, which are those sudden dry spells with much higher than average temperature that can affect there's many decisions in this time period. For example, planting decisions, it could be energy decisions in the energy sector, it could be wildfire related decisions, etc. So we see a need to invest in updating the forecast at the sub-seasonal timescale. And for this, we hope to utilize public data set that's available through what's called the SubX project. And we will look at whether there's some good skill at the 2-week or 1-month time scale in identifying, for example, 500 hectopascal geopotential height anomalies within the May through June to July season. Because as I mentioned before, if you have a high pressure system, it's very likely that you're not going to have rainfall, and that's having a high pressure setup within this season could be the onset of a flash drought, etc. There's work by Kingsley Moore and Dennis Lettenmeyer from 2016, which actually talk about the importance of a high pressure system for flash drought in the south central region of the US. We will also use the Climate Prediction Center's 3 to 4 week experimental forecasts of rainfall and temperature to get some guidance on impending heat waves or rainfall deficits within this time period. And I've provided links to where these products are available. And the CPC uses the sub-X data as a baseline too. So those two, this data set and the 3 to 4 week experimental forecast have some relationship. Then you might wonder, what about other seasons? Because there can be decisions that are equally important that are taken during the fall, winter, and spring seasons, whereas we've only talked about May, June, and July. So for the other seasons, we hope to use rainfall forecast from the North American Multi-Model Ensemble, particularly for the winter season, where these dynamical models are known to have good skill for Texas. I'll wind up with talking about some lessons learned while undertaking this project. So we realized early on that we really could not use the categorical rainfall forecasts for reservoir storage forecasts. We had to come up with a way in which the deterministic forecasts and their associated probability of exceedances could be included. And another really important point that we have to account for is that storage forecasts have to account for local basin conditions. So diversions from reservoirs, reservoir capacity, inflow, etc., varies by reservoir. And there are some reservoirs that are managed as a system. So it's very difficult to apply a generalized formula for all reservoirs, and it is really critical to work with the reservoir operators if forecasts that are of use to them are to be developed, or else, like what we wanted to show was a proof of concept whereby we provide the rainfall information and steps by which they can account for the forecast in their storage calculations so that they can undertake the storage forecast generation themselves, which is actually the preferred format. And lastly, I'd say that reservoir operators need guidance on how they can consult the forecast in a user-friendly manner. And that is the reason we developed those exceedance probability plots for the county level forecast and had the step-by-step framework in which we detailed, okay, this is how you make use of the rainfall forecast in dealing with the CRM output and such. So we had really close dialogue with colleagues at the Brazos River Authority, and most of what we developed was in response to what they felt they needed. To conclude, I'll say that we developed, tested, and deployed this automated tool to provide county-level forecasts for May through July, and it's available at the Water Data for Texas website that the TWDB hosts. And we've demonstrated how the tool could be used to guide the implementation of drought contingency triggers in water supply reservoirs in Texas. We hope to increase the utility of the forecast by updating it at the bi-weekly timescale from mid-May through mid-July. And lastly, we'd like to get your feedback on improvements we could make or on new drought information products you'd like to see, etc. Thank you. And with that, I'll take questions.